Ing highlights the significance of community feedback and collaboration in mastering machine learning concepts. This approach motivates viewers to engage actively and share their insights. The video showcases practical applications of datasets, particularly using the MAGIC Gamma Telescope dataset to predict particle types. This example effectively demonstrates real-world implications of machine learning. Ing clarifies the differences between machine learning, artificial intelligence, and data science. Understanding these distinctions is essential for comprehending the broader landscape of machine learning. Qualitative features are categorized into nominal and ordinal types, each requiring different encoding methods for machine learning models. For instance, one-hot encoding applies to nominal data. In supervised learning, classification encompasses both binary and multiclass tasks, where models predict discrete categories. A classic example includes differentiating between hot dogs and pizzas. Regression tasks aim to predict continuous values, necessitating models that output numerical data. Common examples include forecasting prices or temperatures using various features. The validation set provides a crucial reality check, evaluating the model's performance on unseen data during training. This step ensures the model does not simply memorize the training dataset. Various loss functions, such as L1 and L2 loss, quantify the discrepancies between predictions and actual values. Each function possesses unique characteristics that influence model training and assessment. Accuracy complements loss by offering a percentage of correct predictions, serving as a straightforward measure of a model's performance within classification tasks. Scaling data frames involves calculating the mean and standard deviation for normalization, standardizing features to enhance model training. This step ensures consistency across the dataset. Oversampling techniques, such as random oversampling, are vital for balancing class distributions in datasets. This balance is particularly important when addressing imbalanced classes to avoid bias. Employing k-nearest neighbors, KNN classification, the algorithm predicts labels based on proximity to nearby points. This method relies on distance calculations to categorize new data. The KNN algorithm utilizes distance metrics to identify close neighbors, which can incorporate multiple features for precise predictions. Increasing dimensions enhances the complexity of classifications. Implementing the sklearn library streamlines KNN usage, facilitating rapid model training and predictions without extensive coding. This efficiency reduces the potential for bugs. Evaluation of the KNN model involves metrics like accuracy, precision, and recall, offering insights into the model's performance and reliability in classification tasks. Understanding Bayes' rule is crucial, especially for interpreting medical test outcomes, as it aids in determining the probability of a disease given a positive result. The concepts of false positives and false negatives are fundamental in assessing diagnostic tests' effectiveness and their real-world implications. Naive Bayes classification applies Bayes' rule under the assumption that features are independent, making it a straightforward yet effective method for various classification tasks. The argmax function identifies the class with the highest probability by evaluating each category, which is critical for accurate classifications in naive Bayes. MAP, or maximum a posteriori, is utilized to minimize misclassification probability, assisting in selecting the most likely hypothesis based on available evidence. The video transitions to logistic regression, contrasting regression models with classification. It stresses the importance of accurately estimating probabilities within the model. Simple logistic regression employs one feature, while multiple logistic regression incorporates several features for model construction. This distinction is vital for understanding model complexity. Support vector machines, SVMs, aim to identify the optimal hyperplane that separates distinct classes within the dataset. Their effectiveness hinges on maximizing the margin between classes. The kernel trick is a transformation technique in SVMs that enables nonlinear data to become separable by projecting it into a higher dimensional space, enhancing classification capabilities. Various classification models, including SVM, logistic regression, and naive Bayes, demonstrate differing accuracies. Notably, SVM exhibits superior performance compared to the others. Neural networks comprise input, hidden, and output layers, with neurons processing weighted inputs. Activation functions are essential to prevent them from becoming mere linear models. Training neural networks entails adjusting weights using gradient descent to minimize loss, with the learning rate influencing how rapidly the model converges toward an optimal solution. The architecture of a neural network features multiple dense layers, each with designated activation functions. The final layer employs a sigmoid activation to categorize outputs into binary classes. Compiling the model is crucial, defining the optimizer and loss function along with metrics like accuracy for enhanced evaluation during training. The training phase involves fitting the model to training data while also validating its performance. Adjustments to parameters, such as batch size and epochs, optimize results. The evaluation of the model's performance centers on validation loss and accuracy, underscoring the importance of these metrics in determining model efficiency and generalization. The video emphasizes the significance of hyperparameter tuning, including learning rate and dropout probability, in enhancing model performance during training. Thoughtful tuning can greatly affect prediction accuracy. An exploration comparing neural networks to other models, such as SVMs, reveals that while neural networks possess considerable power, alternative models may be better suited depending on the scenario. Simple linear regression examines the relationship between a single independent variable and a dependent variable, predicting outcomes based on that solitary predictor. This method serves as a foundation in statistics. Multiple linear regression broadens this concept to incorporate several independent variables, accommodating more intricate relationships and predictions. Each variable contributes coefficients to enhance predictions. Key assumptions underlying linear regression include linearity, independence, normality, and homoscedasticity. These criteria validate the model and ensure the reliability of predictions. Root mean squared error (RMSE) offers improved interpretability over MSE by expressing errors in the same unit as the output variable. This clarity aids stakeholders in grasping prediction accuracy. The coefficient of determination, R superscript 2, is a pivotal metric derived from RSS and TSS, indicating the proportion of variance explained by the model.
A hic her R quadrat signifies A beta fit.
Adjusted R superscript 2 accounts for the number of predictors within a model, offering a more accurate assessment as additional variables are included. This adjustment prevents misleadingly high R superscript 2 values due to overfitting. The presenter articulates the necessity of indexing data by specific hours to streamline analysis. By focusing on noon, they adjust the data frame accordingly. Various weather factors are examined for their impact on bike counts. The presenter identifies significant features while deciding to exclude less relevant ones, such as wind and visibility. The video illustrates the process of dividing data into training, validation, and test sets for modeling. This step is essential for assessing the linear regression model's effectiveness. Understanding the assumptions of linear regression is vital for determining its applicability to specific datasets, significantly influencing overall model performance. This consideration shapes the choice of regression techniques. Performance metrics like R-squared offer valuable insights into model efficacy, guiding adjustments to improve predictions. Ongoing monitoring of these metrics remains critical throughout model training. Implementing neural networks for regression tasks signifies a remarkable leap in machine learning, enabling the capture of more complex data relationships. This approach may lead to heightened model accuracy. The video outlines the process of fitting a model using a comprehensive dataset containing all features, emphasizing the importance of thorough model training for precise predictions. Mean squared error is presented as a vital metric for evaluating model performance, facilitating direct comparisons between a linear regressor and a neural network. Mastery of this metric is crucial for informed model selection. The video transitions into unsupervised learning, introducing k-means clustering as a method for detecting patterns in unlabeled data. This highlights the flexibility of machine learning techniques beyond supervised learning. The necessity of recalculating centroids is emphasized, as this process adjusts cluster boundaries based on data points assigned to each cluster. This recalibration occurs iteratively. Expectation maximization consists of two primary steps: the expectation step, which assigns points to centroids, and the maximization step, where new centroids are computed. This cycle continues until convergence is achieved. The video also presents principal component analysis, PCA, as a technique for dimensionality reduction, facilitating the visualization of data spread in lower dimensions.
PCA identifies the direction of maximum variance in the dataset.
Understanding PCA necessitates knowledge of linear algebra concepts, such as eigenvectors and eigenvalues, which are essential for calculating the dataset's principal components to achieve effective dimensionality reduction. PCA enables the visualization of high-dimensional data by projecting it into lower dimensions, simplifying data interpretation while retaining critical information. This method is vital for managing datasets with numerous features. Clustering techniques like k-means can be effectively combined with PCA to enhance dataset analysis, fostering improved differentiation between classes and better visualization of clusters. The comparison of predicted clusters reveals that k-means can accurately group data points, even when labels are not directly related. This flexibility underscores the algorithm's adaptability. By visualizing data in 2 dimensions, the effectiveness of k-means in differentiating clusters becomes more apparent, uncovering insights that may be obscured in higher dimensions. Overall, PCA, or principal component analysis, serves as a method for dimensionality reduction, crucial for effectively visualizing and comprehending complex data structures.